Good afternoon, dear students. Good afternoon, dear students. Let us try to come for today. Actually, we have been done with the topic called as of your rain and river problem and rain and umbrella problem related to your relative velocity concept particulation. Today, let us try to have a small discussion related to your thermal expansion of a solid, where we generally get a good questions for the means and as well as of your neat particulation. So, let us try to talk about the solids parts. You know that whenever you give the heat for any solid, there will be expansion in all the 3 dimensions particulation. If there is an equal expansion in the x-axis, y-axis and z-axis, they are called as of your isotropic solids. That is, if alpha x is equals to alpha y is equals to alpha z, that is known as of your what for me? Isotropic solids. They are called as of your what? Isotropic solids particulation. In the same way, if I am talking about, like say, if alpha x is equal to alpha y and alpha y is not equal to your alpha z, or else if I am writing the relation alpha x is not equal to your alpha y, but alpha y is equals to alpha z. So, they are called as of your anisotropic solids. They are called as of what? Anisotropic solids particulation. And in this one, we have 3 types of expansion. As usually, you know, it is known as of your coefficient of linear expansion, areal expansion, and as well as of your volume expansion. So, if I am going for the linear expansion for 1D dimensions, alpha is equals to your change in length by your original length into temperature difference. For 2 dimensions bodies, if I am going, beta is equals to your change in area by your original area into your temperature difference. And for 3 dimension bodies, if you are going, gamma is equals to your change in volume by your original volume into your delta T particulation. Now, if I am talking about the fractional changes in this one, if I am talking about your fractional changes depends upon only on the material and as well as of your rise of your temperature or difference of your temperature, and it is independent of your length. Like say, if I am talking about your fractional change, delta L by your L will be equal to your alpha into delta T, and delta A by your A is equals to your beta into your delta T. The same way, delta V by V is equals to your gamma into your delta T. That means fractional changes are depending upon the material and as well as of your difference of your temperature, or temperature difference, we can say particulation. The same way, if he is asking the percentage changes, I can just multiply it with your 100 and on both the side, we will be getting the percentage change in the fractional change. So, percentage change in the fractional change is calculated by the formula delta L by L into 100 is equals to alpha into delta T into 100, delta A by A into 100 is equals to beta into delta T into your 100, and delta V by V into 100 is equals to gamma into delta T into your 100. These are some of the basic things which you already know basically. Now, if I am talking about the relation between alpha, beta and gamma for isotropic solids, particulation, you already know that relation between them is given by the relation beta is equals to 2 times of your alpha, and gamma is equals to 3 times of your alpha, or this can also be written as of your alpha plus of your 2 alpha. That means this gamma value can be written as of your gamma value is equals to your alpha plus 2 times of your alpha. 2 times of your alpha is nothing but how much for me? Beta. So, gamma is also equal to your alpha plus of your 2 times of your alpha particulation. That is nothing but 2 times of alpha is nothing but for me how much for me? Beta. So, this is beta, I can write here, this is nothing but of your beta. Gamma is equals to your alpha plus of your beta particulation. So, if I am taking the ratio of this one right now, alpha is to beta is to gamma, alpha is to beta is to gamma is equals to 1 is to 2 is to 3, 1 is to 2 is to 3, or else even I can write from this relation right now from the given part, beta is equals to 2 times of your alpha value is equals to how much? From this one I can write gamma by 3, that means this is 2 times of your gamma by 3. This is also one of the relation between the beta and as well as of your gamma value, or else I can write gamma value is equals to 3 by 2 times of your beta, part, gamma value this 3 beta by your 2. This is also one of the relations which you should be remembering for your competitive examination. But now for the competitive examination, what is very important for is nothing but of your expansions. Like say for example, if I am heating this body right now like this, say for example, this is your metal plate, This is your metal plate. There is a small hole in this one. There is a small hole in this one, and there is one more hole in this one right now. From here to here, this radius is, say for example, R2, and from here to here, this radius is, say for example, of your R1, and the distance between them is, say for example, of your D. The distance between them is nothing but a D, and this is a totally a metal plate. This is totally a metal plate of this one relation right now. So if I am talking about this metal plate, this is consists of your n number of your atoms present in this one. The moment we heat it, the moment we try to heat it, the moment we heat it, what is happening, or when we raise the temperature of that one right now, so what is happening to the value of your R1? What is happening to the value of your R2, and what is happening to the value of a distance between them? So when you give the height to this metal plate, the metal plate is consisting of your n number of your atoms. So each and every atom is increasing. So because of that one, the plate dimension is also increasing. When the plate dimension is increasing, the distance between R1 and R2 is also increasing. R1 is increasing, and as well as of your R2. That means whole of the bigger one is increasing. So R2 increases. R2 also, R1 is also increasing. Thus the total plate is increasing linearly, and as well as of your in the horizontal and vertical direction, the distance between the two holes is also increasing. That means I can write the answers right now here. R1 increases, R2 increases, and D is also increasing. D is also increasing in the given condition. In the same way, if I take one more example right now for here right now. Say for example, if I am taking a concentric circle like this. A concentric circle like this, and this is having a radius, say for example, of your R1, this is having a radius of your R1, and this is having a radius of your R2. So when you are heating it, so when you are heating is this one with a certain external source right now, so what is happening to the value of your R1, and what is happening to the value of your R2, and what is happening to the difference of this radiuses for the concentric circle? So I am trying to talk about right now for your concentric solid sphere or concentric solid bodies, whatever the given conditions we are taking right now. So when you heat this concentric body, when you are heating this concentric body right now, so when you heat it, the atoms present in this one, each and every atom will be the distance, interatomic distances increases, and because of that one, the total diameter of the outer part increases. So R2 value increases, R1 value also increases. So from this one, when you are heating it, no doubt R1 is increasing, R2 is also increasing. What happened to the difference in this one? What happened to the difference in this one? Obviously the difference is also increasing. The difference is also increasing. So when you are heating it right now, actually what is happening? Like say initially R1 is equals to your 10 and R2 is equals to your 20. Difference of this one is nothing but how much for me? Your 10 you will be writing. After heating, like say R1 is equals to your 11 and R2 is equals to, say for example, some 25. Obviously R2 minus of your R1 is greater than this value of this given condition. That is the reason R2 minus R1 is also increasing when you give certain amount of your heat. This is a rough idea I have given for you. Actually it is not required for your basic condition. So R1 is increasing, R2 is also increasing. In the same way R2 minus of your R1 is also increasing for the given condition. I hope you got some of the relations related to your thermal expansions of your solids. Now come to the very important point right now for your see. Say for example, we got two materials. Say for example, we got two materials right now. This is, say for example, one rod of length, say for example, L. And this one is, say for example, another rod, say of same dimension, that is nothing but of your L. Coefficient of linear expansion of this one is alpha, and this one is also your alpha part of relation. And temperature difference for this one is delta T, and this one is also your delta T part of relation. Now what happens for these conditions when you are giving same amount of the heat, when you are giving the same amount of your temperature difference right now for this one, not heat, sorry, when same amount of a temperature difference is being given. One is, say for example, this one is nothing but of your thin rod, this one is your thin rod, and this one is nothing but of your thick rod. This one is nothing but of your thick rod. One is thin rod, another is a thick rod. Both of them is having the same length. Both is having the same length, both of them are made up of same material, and you are giving same temperature difference between them, but one is thin and one is nothing but of your thick. The expansion is more in what right now? So can I say that is nothing but of your expansion of your thin rod, expansion of your thin rod will be equal to the expansion of your thicker rod, will be equal to your thick rod part of relation, because it is made up of same material. Alpha value is also same, delta T is also same. That is the reason I can say that delta L of your thin rod will be equal to your delta L of your thick rod. That means expansion in both of them will be remaining for me same part of relation. In the same way, if I take one more condition right now, now see here, we are giving here right now same temperature, we are giving right now here same temperature. Now same way, if I am taking one more case right now, beta, this one is having a length, say for example L, coefficient of linear expansion is nothing but of alpha, and temperature difference for this one is nothing but of your delta T. And say for example, we got another rod right now. This rod is right now, say for example, of your thick, and this rod is nothing but of your thin. Same length, same material, and temperature of this one is, say for example, of your delta T. Now see for example, if I am giving the condition right now for this one, say for example, if same amount of your heat is given for me, same amount of heat your heat is given, same amount of heat is been given, then expansion is more in what? Either it is in the thick rod or either it is in the thin rod part of a relation. So the combination you see right now, what is the difference between these two? In the first one, we got a thin rod, another one is nothing but of a thicker rod. Both of them are having the same length, same material, so same coefficient of linear expansion, and temperature difference is also same. So when you are applying the same amount of the heat, the expansion in the thin rod will be equal to thicker rod. Generally the students will be feeling that as it is a thin rod, so energy will flowing in the larger way. That is the reason there will be more expansion in the thin rod compared to the thick rod. But that is not happening. Reason for that one is right now, length is same, the coefficient of linear expansion is also same, and temperature difference is also remaining for them to be the same. That is the reason the expansion in the thin rod will be equal to expansion of your thick rod. Whereas in this condition right now, this is a thin rod of length L, this is a thick rod of length L, same material, and we are giving same amount of heat right now for this one. So what will be the expansion in this one? That means delta L will be equal to your how much? How do you write the delta L? Delta L is equals to your original length into alpha into your temperature difference. As the material is being right now for me same, so this one is same right now, this one is also same right now for me. That means I can write from this one, delta L is, the expansion is directly proportional to your delta T. This is directly proportional to your delta T part of a relation. So when you are giving same amount of your heat, I am using the word right now, heat right now means Q is equals to M into S into your delta T, M into S into delta T right now. So for example, when same amount of the heat is given right now, material is same, so specific heat is also same. Now what is the relation between them right now? Delta T, if I am taking out from this one, delta T is equals to Q by your M into your S. As it is made up of same material, so same amount of heat and same speed, that means delta T is inversely proportional to your mass, inversely proportional to your mass. So right now I can write from this relation, delta L is inversely proportional to your mass, inversely proportional to your mass part of a relation. That means in the thin rod and thick rod, mass of the thin rod is less, mass of the thicker rod is been lesser right now. So lesser the mass, more will be the expansion. That means I can say that delta L of your thin rod, expansion in the thin rod, is greater than of your expansion of your thicker rod part of a relation, because it is inversely proportional to the temperature, is inversely proportional to your mass. So lesser the mass, more will be the expansion. So thin rod is having the lesser mass, that is the reason expansion is more in the thin rod compared to your thicker rod part of a relation. I hope you got an idea related to that one. See, even if I am taking one more example, like say for example, if I am giving you an hollow sphere, if I am giving you right now say hollow sphere and as well as of your solid sphere, hollow sphere and as well as of your solid sphere, and same amount of material. That means for them they are made up of your same material and same dimensions part of relation. So when you are giving the same amount of your heat, so obviously mass of the hollow sphere is lesser than the mass of your solid sphere. So can I say that expansion in your hollow sphere, expansion in your hollow sphere is greater than of your expansion in your solid sphere, expansion in your solid sphere part of a relation. I hope you are clear. We are writing that one from this relation. Expansion is inversely proportional to the mass when you are giving the same amount of your heat, when we are giving the same amount of your heat part of a relation. So there are some of the terminologies which should be remembered to do the problems related to your thermal expansions part of relations. Isotropic, anisotropic, relation between them, that is nothing but of your, this is for one dimension body, this is for two dimension body, this is your 3-dimension body. Alpha is known as of your coefficient of linear expansion, beta is known as the coefficient of areal expansion, and gamma is the coefficient of your volume expansion part of a relation. Fractional changes, I told you, delta L by L is equals to alpha into delta T. He may be asking a theoretical question, what is that? Fractional length will depend upon, is it depending upon the initial length? No, it is independent of their initial dimensions of the length, initial dimension of area and initial dimension of your volume. It just depends upon what temperature you are giving to that body and what type of material it is made up of, like say alpha, beta, or say for example gamma part, whether it is 1D dimension, 2D dimension or 3D dimensions. The remaining all other derivations I have done it very clearly, and this is a very important area right now for competitive examination, especially for the means and need. These are the important area where you need to keep the difference in the mind very clearly. What exactly is the same temperature, what exactly is the same amount of the heat. When I am applying the same amount of the heat, I am using the formula Q is equals to ms into delta T. So temperature is inversely proportional to the mass. So that is the reason expansion is inversely proportional to the mass. So lesser the mass, more will be the expansion part of relation. So that was something related to your what you call the thermal expansions of your solid. If you need to do some of the problems on this one, so try to concentrate the problems on your isotropic and as well as of your anisotropic solids right now, and some of the concentric shells of the given condition. And even we have something related to your right now called, say for example, thermal stress. There is also one more term called as of your thermal stress. Thermal stress. Thermal stress is nothing but what? When a rod is being fixed between two rigid supports. When a rod is being fixed between two rigid supports, and when you are giving the certain amount of heat, there is a small bending seen in this one because of your stress developed in that one. That is given by the relation y is equals to your thermal stress divided by your thermal strain. Stress is nothing but right now thermal stress. If I am writing thermal stress is equals to y into your thermal strain. What do you mean by strain, beta? Change in length by original length. So it is y into delta L by your L, that is equals to y. Delta L by L can be written as of your alpha into your delta T. So this is your thermal stress part of relation. If I need to calculate the force, force by area is equals to y into alpha into delta T, or else force will be equal to y A alpha into your delta T part of relation. These are also some of the important relations you should remember for your competitive examinations part of relation. I hope you got some relations related to this one. Today it has been little bit late with respect